Everyone, welcome back to the centripetal force continued lesson. And so in the previous lesson we had come up with two different types of equations. One for when we're working with a horizontal system where we have some frictional force affecting our scenario, and in the second second situation when we're looking at the a vertical system, we came up with a equation where we were looking at just speed. And now we're going to look at an example actually applying that equation. So a 700 kilogram roller coaster full of people goes around a vertical loop that has a diameter of 50.0 meters. What minimum speed must the roller coaster have at the top of the vertical loop to stay on the track? So as always, I'm just going to start off by writing down all the information that I have. So I know that my roller coaster is full of people has a mass of 700.0 kilograms. And we know that it has a diameter of 50 meters, which we know that just working with our equations, we know that our radius is a more useful value to work with, so we're actually going to find that radius here. So your radius is half of your diameter, so you're going to divide that by 2. And so we get 25.0 meters for our radius. So then in order to find our minimum speed, we're actually going to use that equation we came up with at the end of the last video, which was speed is equal to the square root of the acceleration due to gravity times the radius. So actually in this case here, our mass has no effect on our speed. So we can plug in all the values that we know. We know that gravity on Earth is 9.81 meters per second squared. And the radius here was 25.0 meters. So you can, if you want, you can either plug all this into your calculator at once, or you can simplify under your radical, which is what I will do right here. So we have 9.81 times 25.0, which if you plug that into your calculator is 245.25. And I'm going to make sure I account for sig figs here. So I just need to make sure I keep the same value for our radius. So this one here had 3 sig figs, so our answer here is going to have 3 sig figs as well. And now we can go ahead and plug this into our calculator. So we're going to take the square root of 245.25. And so what we should get on in our calculators is 15.660. I'll make sure to account for my sig figs here. So I had 3 to begin with, so my answer should have 3, meaning our speed will have a final answer of 15.7, and our units are meters per second. Here, if you guys notice, we're working with kilograms, we're working with meters here, so this would indicate that our speed should be meters per second. And then just to finish this off, we are going to write this as a sentence. So in order for the roller coasters to stay on the track, it must have a minimum speed of 15.7 meters per second. Alright, so now we're going to look at another different type of case when we're working with a vertical system. And this just has to do with when we have something that is connected to the object that's traveling in a circular motion. So what happens when we swing a pail of water around in a circle? If you guys actually haven't done that, you might want to. It's go out on a nice summer day. Make sure you're doing it outside, away from technology, in case you don't swing it fast enough. But if you were to swing it fast enough, the water will actually stay in the pail, and you will not actually get wet. So this type of situation is different from a roller coaster because now we have a tension force that's acting on the pail by a rope. And so we really have 3 different scenarios when we're working with, say, a circular motion that's in a circular or a vertical system, and we have some sort of object or something's going on that's acting as a bit of a tension force, say like a rope. So our first example here is when your bucket is straight above from where, say, I guess that would be from where you are, or from whatever object it is swinging in. So in this case here, your centripetal force is equal to your force of gravity plus that tension force. And so these ones here both be the same values here, so you would add these two together. In a case where maybe you're working with an object when you're swinging it, that it's directly to the left or directly to the right, that is just where your centripetal force is equal to your tension force. And then our last little scenario here is where we have our centripetal force is equal to, so it's that tension force provided by the rope and the gravitational force, but in this case here, these two are opposite, so you are still going to add the two together. So your centripetal force is equal to that gravitational force plus that tension force. But in this case here, gravity will be negative and then your tension force will be positive because they're acting in two separate directions there. So just be very careful when we're working with a vertical system and we have some sort of tension force from an object like a rope. You have to be very careful because that centripetal force depends on where that object is located. So in the case of when it's straight up or straight down, it's your gravitational force plus the tension force. And when it's left and right, or left or right, it would just be the tension force. Gravity's just pulling it down, not affecting that inward force or the centripetal force. So that's why we only consider that tension force. So let's look at some examples where we have some tension force working in a vertical system. All right, so a bucket of water with a mass of 1.5 kilograms is spun in a vertical circle on a rope. The radius of the circle is 0.75 meters, and the speed of the bucket is 3.00 meters per second. So what is the tension of the rope in position C as shown in the diagram below? So position C is this value right here. So this here is where your bucket is straight below from whatever center of this circular motion is providing. So if you guys remember this, when we're working with a, I guess when we're looking at centripetal force and it's straight down, that is equal to your, so it's the gravitational force plus that tension force. So there's going to be a force pushing up and a force pushing down. So your gravitational force here is going to be negative, while that tension force is going to be positive as they're moving in two different directions. All right, so in this question, we are looking for what is the tension on the rope. So we're actually looking for this value right here. And so what we can go ahead and do is we can actually plug in some different equations that we know for centripetal force and for a gravitational force. And I'll just write this over here. So your centripetal force is equal to your gravitational force plus that tension force. And I'm going to substitute in my equation for centripetal force, which, if you guys remember, is your mass times your speed squared divided by your radius. And your gravitational force is your mass times the acceleration due to gravity. And then we can just add it with that tension force. So next what we can do is we can write down all of the information that we're given in the question, or you could have done that just to begin with. So here we have a mass of the bucket is 1.5 kilograms. So it says the radius of the circle is 0.75 meters. And the speed of the bucket is 3.0 meters per second, or 3.00. If you guys want to, you guys can also include that gravitational acceleration, which we know is 9.81 meters per second squared. And in this case here, it's going to be down. So then we can go ahead and plug in all of our values into our equation, and we can solve for this tension force. So your mass was 1.5, your speed was 3.00, and that value is squared, divided by your radius, which was 0.75. That's equal to your mass, which was 1.5, times the acceleration due to gravity, which remember this one here is coming down, and these are opposite directions, so that means that this gravity needs to be negative, so negative 9.81, and then plus that tension force. So first we should work on, let's clean this up. This looks pretty horrifying with all these values, squares, dividing. That all just looks pretty crazy. So let's simplify this a little bit. So if you guys want to, you guys can plug this all into your calculator all in one step. But let's simplify this left-hand side. So go 1.5 times 3.00 squared, and then divide it by 0.75. Just be very careful that this square only applies to the 3, so you might need to include some brackets in your calculator. But if you plug it into your calculator, we should actually just get an answer of 18. And I will account for my sig figs here. I've got 2 sig figs in the 1.5, 3 in the 3.0, and 2 in the 0.75, meaning my answer will just have 2 sig figs. So that actually worked out really nice. So now simplifying this gravitational force, we're going to go 1.5 times negative 9.81, and that is negative 14.715, and then plus a tension force. Alright, so I'm actually running out of room on this page, so please, if you need to, pause the video, write down your work, and then I'm going to erase it here in just a second, and we will start back at the beginning of that little section there. So pause it right now if you haven't. And well, bam, it's erased. So one thing I did forget to do at the bottom here before I erased everything is I forgot to count for sig figs for our 14.715. So in the previous work we had 1.5 times negative 9.81, and we accept gravity as it is, so we just had to really work with this mass of 1.5. So this one here had 2 sig figs, so our answer should have 2 sig figs there as well. Alright, so jumping back here, we need to solve for this tension force, so we need to get rid of this value right here. And so this is a negative 14.715, so to get rid of that, we can just add it on both sides. And so adding them together, we should get 32.715 is equal to that tension force. And we just have to be a little bit careful here because now we're working with our adding and subtracting rule for finding sig figs. So we have to go to our least precise value, which actually in this case here is kind of nice because they're both in the ones position, meaning our answer should be in the ones position as well. So our answer for our tension force is 33, and our units here are newtons for force. And in this case here, we can include a direction in this case because we know that the tension force, when you're working with an object at the very bottom in the circle, would be going straight up. So when we're including our sentence, we can make sure to include the direction there as well. So the tension on the rope is 33 newtons, and our direction here is up. When we're working with either going straight up, straight down, left or right, then that one there is kind of nice because we do know which direction the tension force is going, especially in our diagram here. It even shows us the direction, so please make sure in this case here you are going to want to include your direction, as force is typically, and I say typically, a vector quantity, so in most cases you really should have a direction there, okay? Alright, so I'm running out of time on this video, so we are going to pick it up in the next video, and hopefully we will be able to finish off that lesson in the next video.